In this video, we're going to talk about hash tables. Hash tables are not in the textbook, so I've released this document that you're looking at as a PDF on the course website as well. So hash tables are a natural extension of the searching and sorting that we just covered in the last chapter. So remember, with searching, we have two basic types. If we have unsorted data, we have to do a sequential search where you go through and start at the beginning and go through until you find what you're looking for. So with that, you could take up, if you have 100 elements, you could take up to 100 comparisons if the item's not found or if it's the last item in the list. If you have a binary search, it's better in that you use a binary search on sorted data. So with the sorted data, you'll go to the middle of your structure of the table and then see, is it bigger or smaller than this? And you can narrow things down in that way. So you get significantly fewer comparisons on that. But hash tables can be even more efficient. Okay, so the idea behind a hash table is that we're going to store our information in an array. The position we store each bit of information in is going to be determined by a hash function. Okay, so it means basically we can compute where exactly each piece of data is going to be. Okay. And we'll see some examples for this to make more sense. So therefore, the search will be, if you think of it as if you're at a warehouse full of like a storage place with all the little garage doors, if you can put in what you're looking for and it tells you exactly which garage door to open, that's the idea. Okay. And there's some challenges with this that we'll talk about. So um, the hash function then is going to be the way to take some value, some key, and it's going to return an integer, which is the position we want to store that value in. Okay. So in the simplest example, if we have 10 buckets, we call them 10 buckets in our array. So our array length is 10. If we would take an integer we want to store, like 25, do a modulo 10 or a mod 10 on that, a mod 10, 10 being the size of our hash table. That's a simple example because that just gives you the ones place of that. Okay. So I forgot what my example this was, but let's say it's 29. So 9 would be the answer when you do 29 mod 10. Okay. So 9 would be returned by the hash function as where we're going to place that data. So we would go to bucket 9 and put 29 there. Okay. So that's the basic idea. Okay. Um, the problem with this, we'll get into in a minute, is you can have a collision. Okay. So if, for example, you would never have a hash table of only 10, but 10s makes it convenient. So if we store 29, it goes in bucket 9. Okay. Let's take a simpler example. 25 gets stored in bucket 5. Okay. So we now try to store 35. 35 would also get stored in bucket 5, or you try to, but you can only store one thing in a bucket at a time. Okay. So what do? You have a collision. Okay. And what you do with the collision is going to give us the different types of hash tables that we can have. Okay. So the two main types, as it shows here, we've got the chaining, we've got the open addressing. So, and each have pros and cons. So with the chaining, in each of our buckets, we put a linked list. We've covered linked lists. We know how that works. So with the linked list, we can of course store as many things as we need. So if I put 25 goes in bucket 5, it becomes, if the linked list is empty and 25 is the first one, it becomes the first element, the first node of the linked list in bucket 5 contains 25 and a null pointer. Okay. If we go to add 35, we go to look and see, well, there's already something in bucket 5. So the first node's not empty. So we move to the second node. We now have a linked list, 25 at the head, and we have 35 at the end. Okay. And then when we go to search for it, of course, we know if we're looking for 55, we would run that through the hash function to give 5 as a value. We would look and say, okay, is it at our first node? It's not. We would continue down, so it's not 25. Go to the next node. It's not 35. Now we're done. It's not found. Okay. So it speeds things up a lot. Okay. So once you have these linked lists, you can add to the end, you can delete, you can do whatever we normally do with linked lists. Okay. The other way to go, and we're going to look at in code first, is open addressing. So open addressing, if you go and if you're trying to store, 35 in your list where 25 is already there, it returns, okay, it should be in bucket 5. When you look in bucket 5 is not empty. We're just going to move to bucket 6 and store it there. Okay. Keep moving until it's not empty. Okay. This will decrease our efficiency on search in that creates what we call a chain, where if I store a 25, a 35, a 45, that would get stored in buckets 5, 6, and 7. Okay. Then if I was looking for the 45, I would have to go to bucket 5. It's not there, move to the right. Okay. And you would keep looking until either you found what you were looking for or you hit an empty cell. If you hit an empty cell, you knew you were out of luck. Okay. But that can get confusing in that if we have 25 in bucket 5, 26 or 20, sorry, 25 in bucket 5, 35 in bucket 6, 45 in bucket 7. If we would try to store 27, it would want to go in bucket 7, but we'd have to put it in bucket 8. So things can get moved around a lot with the open addressing. Okay. So that's called linear probing, where you add one. There are more complicated ways to determine which cell to put things in to try to space things out more evenly in the table. Okay, those are called quadratic probing. Well, they're basically going to create a function that you put the value through that's not a modulo function, but it's going to spit something back out that's an integer in the right range. Okay. With this open addressing in particular, we have to worry about the load factor. So the load factor is the number of elements divided by the number of buckets. Okay. With the open addressing, since we only get one item per bucket, that can be difficult. If it gets too full, then it's going to not be very efficient. In general, they say that it should be less than half full in order to have some efficiencies. Okay. So with the chaining, it's not such a big deal because you can put as many as you want. Okay. With chaining, the longest linked list becomes the efficiency limiter there. Okay. So let's take a look at implementing the open addressing using linear probing. Okay. So again, for simplicity in our example, we're going to assume that our hash table size is 10. You want to store that in a global constant called hash size or table size, whatever you want to call it. By making it a global constant, remember that's a variable that's declared with the const keywords for constant, and that it's declared outside of any functions. So it's before the main function, before any other function you develop. Okay. That way you can get to it from everywhere. We have it in all capital letters because by convention, all capital letters denote a constant. Okay. So we're going to use the modulo function again, which will place integers in, or place the integer values that we're trying to store in the buckets 0 through 9. Okay. The modulo function again, if you have whatever number, if you have 23 mod 10, it takes 23 divided by 10, which gives us 2 with a remainder of 3. The modulo returns that 3. It's the remainder. Okay. So in essence, a mod 10 will give you just that ones place. So I've got some examples here. 5 mod 10 is 5. 123 mod 10 is 3. Okay. So in implementing this, we want to be able to track when a cell is empty or not. Okay. So we want to initialize our table to some value. And what we're going to do in this case, we're going to use a -1 to show empty. So I've created this function here. Okay, here's our hash function. Okay, then we'll do our initialization. The hash function here just takes an integer value. It's going to return that value mod the hash size. Okay, that's all that does. So we can loop through and set all of our array positions, or all of our buckets are set to -1 when we start. Okay. So if we wanted to add a 55 to the hash table, we run that through the hash function and get back a 5. Okay. So we can now set table 5 equal to 55. Okay. So here's our new modified table with 55 in the 5 spot. Okay. Again, we talked about a collision. So if we do something else that ends in 5, it would have the same value returned from the hash function. Okay, so we have a collision, so you have to move it to the next bucket. So in this case, we're adding 125 to our table. When we do that, 5's the key as well. So now we see that it's now in position 6. Okay, we had to check here. Okay, does cell 5 equal to -1? Is it empty? No, it's not. So let's move to here. Does cell 6, bucket 6, equal -1? And it did. So we placed the 125 there. Okay. So we're going to add 2 more elements here. We have something that we haven't talked about yet, and that's the wraparound we need. Okay. So if we're going to add 19 and 329, 19, the hash function will return a 9. Okay. So it's going to go in this 9th bucket. No problem. Okay. The problem is that when we get to 329, we go, okay, it should be in bucket 9 as well, but this is full. We can't go to the right any further. What do we do? Well, what we do is we come back around to 0 and see that, yeah, that's going to be okay. Okay. So we're going to use a modulo again, basically. So anything past the end wraps back around. Okay. So I've got the example here of how we would do that. I've got while the table key is not equal to -1. Okay. So I'm looking for a spot to put my value in. So I got to keep going until I find the -1. I'm going to increase the key by 1 and then take that mod hash size. So if here I'm at 9, and I'm going to say the key is equal to 10 mod 10, which takes us back to 0. Okay. And that will correctly find this next spot in the hash table. Okay. So again, we go to search. If I'm searching for 55, I go right here, it's there. If I'm searching for 125, it starts in bucket 5. It doesn't find it. It goes to the right. Now it finds it. If I'm searching for 35, it's going to go to bucket 5. It's not there. It goes here. It's not there. It goes here. Oh, this is empty. Now it knows it's not going to find it, and it can stop. Okay. So that's the basic idea. Okay. We do have a problem that we need to think about, though, that if there are no empty buckets in the hash table, okay, we would keep moving. There's a risk whenever we wrap around the list that we're going to go around forever. Okay. So if we have a totally full, all the buckets are full, I go to insert. I'm going to keep in that loop, keep looking. So in this loop here, I'm going to keep looking for there to be a -1. If this is never true, then we're in an infinite loop. Okay. So that is a problem. Okay. So what we'll do, and we haven't talked about search yet. We'll talk about search later, but we're going to use it anyway, since we're going to be doing it in a second. So we're going to basically do a search to see if a -1 is available. Okay. So if there's no -1, we're not going to go through that same thing we were doing before where we're looking for a -1. Okay. We're just going to return that the table's full. Okay. In practical usage, your hash table should never be anywhere close to full, but this protects us if it is. Okay. Now we have to think about what we're doing to delete an item from a hash table. Okay. So you may think, since it's an array-based structure, it's pretty straightforward. We just change it back to -1. Okay. And we could do that. Okay. So here's an example where we're going to delete 55. We run 55 through our hash function to return that it should be in bucket 5. We look, yep, it's there in bucket 5. I'm just going to change that to a -1. Simple enough. Okay. The trouble is, what if I go looking for 125? 125 should be in bucket 5. I look in bucket 5, bucket 5 is empty. So I wouldn't look any further. Okay. So that's a problem. So one possible solution is that I could move the 125 back to this cell and then move anything else that we'd moved back to their original positions. But that turns out to be really messy in code for sure. Okay. So we're going to take a different approach instead. We're going to use a number to denote that a cell has been deleted. Okay. So a cell that has been deleted is empty as far as the using the linked list goes, but it lets us know that we need to keep moving to the right. It's not empty in terms of a search. Okay. So we're going to use -99 to indicate that the bucket has been deleted. Okay. So in the previous example, we've deleted 55. Okay. So if I wanted to add something here, if I wanted to add 75, I could add it right here and it would be fine. Okay. But if I don't add anything and I go searching for 125, I look at this bucket, it's a -99. I know to move to the right. I know that this has not always been empty. Okay. And this is a cleaner way to do it in code for sure. Okay. And I tried to name my function delete, only to realize you can't name it delete because delete in C++ is a reserved word. Okay. So I just called it del. So this is what this looks like. So this is going to take, as most of these are, it's going to take a pointer to our table, to our array. Okay. We pass it by reference. So we can, the changes that are made in the function are going to reflect, and we have some value that we want to delete. Okay. We start all of these functions pretty much with using the hash value to get our key or our index. Okay. We're first going to do a search. We've got search, let's use it to make sure that, and search is a Boolean function. We're going to make sure that what we're trying to delete is actually in the table. If not, it's not worth our time. So we run that real quick, and then we say that that value is not found and can't be deleted. Okay. So another issue that we have here that we're going to talk about here is we want to make sure, and I think this is redundant because we've checked for it. We want to make sure we're not searching forever. Okay, so I'm going to go ahead and create this local integer called one, or called local C, that I'm setting to 1. Okay, and again, I'm talking about this here. If the table's full, we could look forever for this if it doesn't exist. Okay, so I'm just going to put this check in here. Again, I don't think I need it because I'm doing a search first. But basically, as long as the count is less than the hash size, I'm going to keep going. Okay. If not, I'm going. So as long as that's not the case, two possibilities. I'm going to check to see if the table at the index that we want, the key that we want, is equal to the value. If so, then I'm going to change that to 99. It's been deleted. Okay. At that point, I can return. I'm done with the delete function. Okay. If not, I'm going to go ahead and using the modulo operator on hash size, I'm going to go to the next one to the right. Okay. And again, I think this local C in this instance is probably overkill because it would only come up in a full table where the item is not really there. So I don't know that I need it, but it certainly doesn't hurt anything. It's a simple enough check. Okay. So that's how the delete's going to work. We're going to mark it as a -99. Okay. That will lead to a modification in our add, which we'll talk about as well. Okay. So now let's look at our search. Okay. So the search function, we're going to see if something exists there or not. Okay. Again, we're using the linear probing. We're using the open addressing. Okay. So here's the search. We're going to get the key for the value we're looking for to be to search for, not to be deleted. Correct that. To be found, let's say. Okay. We're going to start at that value. We're going to keep looking as if the value that we're looking for, or if the bucket where the value should be is empty, then we know the search has failed. If not, we're just going to move to the next bucket to the right. We're going to keep going, okay, until we hit an empty an empty cell, an empty bucket, a -1. This one we do need the local counter because this one in a full hash table would never have an empty bucket. There would be no -1s. So we're going to go round, round, round. Okay. Again, I probably could have searched for a -1 as well, but I'm in the search already, so I couldn't have done that. So that wouldn't have worked. Okay, so here's our Boolean function, which is search. We're going to take an integer. T is the table we're going to be passing along to the function. It has the asterisk, so we're making actual values to it. It's passing by a reference, not by value. And here's the value we want to search for. Okay. Of course, as always, we get the key first. Here's our local variable being initialized. Okay. So as long as we're less than the hash size, we're going to look to see where that key's at. If we find the value where it's supposed to be, first off, what the key says it is, we're going to return true. Else, if that position contains a -1, we know right away that it's false. Okay. Else, okay, so that's the else if. So if we don't find it and we don't not find it, okay, we're going to increase the key by 1 using the mod on the hash size to wrap around if we need to and increase our local count by 1. Okay. If we get to this point in the code, then we have failed. That means that we have exceeded this this constraint that we've searched for more than there are in the table. Okay. And there we go. Okay. I also added to my code a simple print just to print what's there. You don't normally print a hash table. We don't normally care what's going on inside of it, but when you're coding, it's certainly useful to do that. So I'm just going through and looping to do that. Okay. So then I've created here a test program where I'm going to create a new hash table. Okay. Based on the hash size, I'm going to initialize the table. Okay. Put some -1s everywhere. I'm going to add some things here. I'm going to do some searches and so forth. Okay. So that's the basic idea here. Okay. One thing that I didn't say that I thought I had in my notes, but apparently I didn't, was when we're adding. Do I not have the add function here? That would be crazy. There's the add. Okay. In this add function, okay, I have -1 here. Okay. But in reality, if it's a -1 or a -99, okay, either one's okay. So there would be a modification there. So I would say file that or okay. So I'm looking here if the key. So if, yeah, so this is I wouldn't increase in this case. So T key equal to -99. Okay. So either of those cases, I would be able to add it. Okay. So you should be able to code that in, run the test, and life should be good. That's what I meant to do. Okay. You probably didn't see that anyway. So there's some things we can enhance with our table here. The first is to have the load factor, which lets us measure how full the table is. Table is too full, then we're going to have some performance issues. So when we have a pretty sparse table, there's not much in it, then searches should only take a couple of comparisons. Okay, for our example before, well, in this case, searches should only take 2. Okay, if we search for 55, we immediately know what it is. It would return a true immediately. If we search for any other number that doesn't end in a 5, it's going to immediately find that it's not found. Okay. If it does search it for something with a 5, like it's searching for a 65, there'd be 2 comparisons. It would check this and then check this, see that it's empty. Okay. So if you had a bunch of things that ended in 5, so this would be where you added a 55 first, you added a 75, you had to move it 1 to get to there, you had an 85, 1 over, 95, 105, all the way to 135, it wraps around. Okay. Then in worst case scenario, you would have 8 comparisons to get to this 135. Okay. So we're using super small examples, but if we had thousands of buckets, which is certainly possible, then the performance could go downhill. So you want to make sure that you monitor that load factor, okay, and increase the size if necessary. But increasing the size of a hash table after it's already in production is a pretty involved process. You'd have to remap, you'd have to basically create a new table that's bigger and then remap all of your data. Okay, so you want to try to make your hash table a sufficient size when you start. Okay. So the other way we could do this is, and I'm not going to give this full example of the code, is to use chaining, which use linked lists. Okay. So this is kind of what this looks like. So I've got, again, I'm using a hash table size of 10, which gives me buckets 0 through 9. Okay. Each of these would be a linked list. We start off, I'm using this little symbol here to denote an empty linked list. Okay. So if we were to add 33, okay, we would send that to the hash function, get a 3 back. So I would go to bucket 3 and say, okay, there's an empty list here. So I'm going to add this new node 33. This would point to null. Okay. Then we add a 13. I'm going to go here and say, okay, here's my linked list. There's a node here. It doesn't equal null. I'm going to keep, or this points to not to null. I'm going to go here. This does point to null. I would add that one there. Okay, so the link from this first node points to the second node points to null. Okay, and then we would be done. Okay, so we could continue to add things onto this. If we added a 127, it would go here. You know, if we added 347, it would go there next in line, and so forth. Okay, so then on um, the search, we would have to find the correct uh, linked list and search through the entire linked list. Okay. To delete, we would just do a delete like we would normally do a delete on a linked list. Okay. So again, we probably could extend unordered lists, but like we were doing with the stacks and the queues, that probably leads to more overhead than we need. So I think the best choice here is just to um, implement that same code or the same ideas of the code for what we need um, into the hash table code directly. Okay. So I'm going to give some code snippets here, and then it'll be left to you to create the entire thing. Okay. So the node we're going to need here is going to have a key. Okay. The key is going to be the information that's being stored. Okay. Then we have our next, okay, which goes to the next link. Okay. So seems like we may have called that link in linked list. I don't know. I go back and forth. It doesn't matter. Then we have, of course, here, this is the constructor. I said, of course, we haven't talked about this yet. So we don't typically add a constructor to a struct, but you can. So I thought I would throw that in there. And this is the shorthand constructor that when we create a new node, which is a struct, it's going to go ahead and when you send it an integer, it's going to put that key there and it's going to set the next pointer equal to the null pointer. Okay. So that's just that simplifies our code a little bit. Okay. So the next thing we're going to do is going to create a hash table class. Okay. So this has something we may not have seen before, and in that it has our table is going to be a pointer of pointers. Okay. And this is basically how we denote an array of pointers. Okay. Because the linked list is just a pointer, right? The what we're storing, that's not correct. A linked list is not a pointer. How we address a linked list, the head node we talked about before, the root node. Okay, that's a pointer to the first node. Okay, so we're storing pointers in our table. So this is going to be an array of pointers to nodes. Okay. So again, we have our capacity here. The hash function looks exactly like the hash function always does. Okay. As far as the constructor goes, I'm going to give just the prototypes for this. Okay. So the constructor should set up the basic ideas. Um, for a new one, given a certain size, what should that look like? So you have to make sure you've set up, the linked lists and the array and all that. And then we have the destructor, which is going to make sure everything gets deleted. All the linked lists get deallocated as we go along. Okay. The other functions we have, as before, we have an add, which will take a key and figure out the index using the hash function. It will then go to that bucket and add the key to the linked list. Okay. If it doesn't find anything there, it adds it to the first one. If not, it will add it to the end of the linked list. Okay. The search will take a key and will search the hash. So it's going to run it through the hash value. It's going to go to that bucket. Okay. So whatever the hash function tells it to, it's going to go to that bucket. It will then search that linked list that it finds, see if it finds it. Okay. Boolean function, true or false. Now, delete function will take a key also. It will run that through the hash function to get the index. It then goes to the correct linked list, and then it's just deleting from the linked list like we've done before. Okay. So here are the function prototypes for this. So things that they take, pretty straightforward. So I've left it to you to complete this, the chained hash table code, and write a test program. So in conclusion, the hash tables can increase the efficiency of our searches. Okay. And again, that's because if they're well designed and well implemented, you can more quickly get to where you're going. You kind of know where things should be. Okay. But there are some efficiency issues that we have depending on which type we're dealing with. We've mentioned some of this before. Okay. So open addressing, we'll talk about first. We have the array that holds our elements directly. Okay. So the issues that we have here, we want to make sure that the hash table is big enough. Okay. So as we're doing this, we develop these chains where every time we have to move one to the right, that creates a chain. So the worst case scenario on a search is whatever that longest chain is. Okay. So that's an issue. We also have the issue that we can run out of space. We have to allocate in advance how much space we're going to have. Okay. So these are the things that we have to worry about. Okay. So for this to be efficient, then our hash table should be twice the size of the number of elements we think we're going to store. Okay. So this increases the efficiency as far as performance. So it's computationally less expensive, but it takes more memory. We're taking up twice of what we need, which could be a problem. Okay. So if we're in a memory constrained environment, then using the open addressing may not be for us. Okay. Um, Using chaining, of course, like chaining always is, it's more memory efficient. There's more code involved. The code is more complex, but we're only storing what we need. We only need enough storage for the elements we're storing with just a little bit of overhead. Okay. So the worst case scenario of this is you figure out what's the length of your longest linked list. That's the worst case scenario. Okay. If bucket 5 has 10 items and we're looking for something that should be in bucket 5, then we have to search all 10 of those items in the worst case scenario. Okay. And that's it for hash tables. They're important to know. They get used a fair bit because of their ability to relatively easily index information and get you to it quickly.